Just to review, a parametric curve is a map that maps some parameter that we would call t in most cases to a point in 3D space that has x, y, and z coordinates. So it's like a function that takes in one input variable and that has 3 output variables. Your book sometimes calls this a vector valued function. But as an example, this could be something like cosine t, sine t, t squared. Right, so I have the x coordinate, the y coordinate, and the z coordinate as a function of my parameter. And you would also, in addition to having this function of t, you would generally say, okay, I'm going to allow t to be all of the values between 0 and 3. So you'd also state some upper bound and lower bound on your parameter so that you could tell people where your curve starts and ends. And I think we're already familiar with this because we've already done this a lot. But oops, not y squared, t squared. I said t was going to be between 0 and 3, so I just have to figure that out. Yeah. So there's my parametric curve, parameter t. What a parametric surface is it maps a two-dimensional space. So it's going to map, we usually use the letters u and v for our parameters. And it's going to map this two-dimensional space. Again, it's going to map it into a three-dimensional space with x, y, and z. So we're also going to define a parametric surface with equations where my x-coordinate is a function of u and v, and my y-coordinate is a function of u and v, and my z-coordinate is also a function of u and v, like this. And just like with a parametric curve, we're going to have to specify upper and lower bounds on u. Like we could say u is every value between 0 and 1. We might say v is every value between -5 and +5. But we have to give upper and lower bounds on both of my parameters. So for a surface, since surfaces are two-dimensional objects, we have to have two parameters to define a parametric surface. Curves are just one-dimensional objects, so you only need one parameter to define it. Okay, here's an example. Here's a surface where I say my parameter u is going to take on all the values between 0 and 2 pi. My parameter v is going to take on all the values between 0 and 2 pi. And then I'm going to call my surface little lowercase r, just to give it a name. But again, I'm going to give my x-coordinate as a function of u and v, my y-coordinate as a function of u and v, and my z-coordinate as a function of u and v. And these functions are going to be like that. So my x-coordinate is going to be cosine of u times 3 plus cosine of v. My y-coordinate is going to be sine of u times 3 plus cosine of v, and then my z-coordinate is going to be sine of v. And the way that I try to think about this is I think about a little square. And this square has a direction u and a direction v. And so here is 0, here is 2 pi, here is like pi, and then here's 0, 2 pi, and pi in the u direction. And I think about this being a little like flat piece of square fabric. Like this point on the fabric has the coordinate pi comma pi because the u is pi and the v is pi. But anywhere on this sort of square piece of fabric, you could assign a u coordinate and a v coordinate. And what this function is doing here is I'm taking this flat square piece of fabric and I'm twisting it and I'm stretching it and I'm moving it and I'm rotating it to a different orientation. It's the same piece of fabric, but I'm sort of just manipulating it and deforming it so it ends up somewhere else in 3D space. And if you want to graph this on MATLAB, this is the MATLAB code you would use. So the first 3 lines, I just like to include all my MATLAB codes because this clears the console. It's going to close any other figures you have open, and it's going to clear your variables. Then these 3 lines here with the A, B, and U, comma, B, this is how you tell MATLAB to generate a little square of fabric. So what this is saying is lowercase a can take on all of the values between 0 and 2 pi. Okay? And what this code is actually putting right here is 0 colon pi divided by 25 colon 2 pi. That's what that line of code actually reads. So, good morning. In MATLAB, whenever I say 0 colon pi over 25 colon 2 pi, what that's telling you is the lower bound is 0, the upper bound is 2 pi, and the pi divided by 25 is specifying your step size. So I'm saying give me a mesh of points where there's going to be 50 points evenly spaced between 0 and 2 pi with step size pi over 25 in between each point. Okay. So then I'm doing the same thing with a little lowercase b. It has the same lower bound, upper bound, and the same step size. And then where this says u comma v mesh grid a comma b, what that's saying is a is a one-dimensional mesh of 50 points, and b is a one-dimensional mesh of 50 points. I want u comma v to be a two-dimensional mesh with 50 times 50 points. It has to have 2,500 points in the square piece of fabric that I'm talking about. Okay, and then I have this, and this is actually the equation for the parametric surface right here, where I have x and y and z coordinates as a function of u and v on my little piece of square fabric. And then what comes below this, this is all just code that, first of all, plots it as a surface in 3D space. So that command in MATLAB is surf xyz. The rest of it is just making the graph look nicer, because I don't like the way that it appears by default in MATLAB, and so I always include these lines of code just to like make it look really nice. Okay, but let's plot this, and we'll see what this parametric surface looks like in MATLAB. And to do that, I'm going to go to Chrome, and then I'm going to search for MATLAB Online. I'm just going to copy and paste this code in here. Okay. Copy. See if it works. Okay, so it finally works, and you can see that it's a little torus. It's a little donut. So MATLAB's nice because you can even rotate it and you can see what it looks like. But that is my parametric surface that I got from those equations. And this would be maybe not impossible, but it would definitely be hard to plot as like a explicit or implicit surface, and it's relatively easier to do as a parametric surface. So there's some benefits to doing this that you don't get if you're just trying to plot everything explicitly. So this is what I want you guys to do as part of your homework. I want you to like use this code, copy and paste it into MATLAB, but then see what happens if you try other commands or other formulas for x, y, and z coordinates, and see if you can make like a really cool looking surface. Here's another example. So this is another surface where I'm allowing my parameters u and v to be between 0 and 2 pi and 0 and pi. This time, I've got a new formula for my x, y, and z coordinates. It's a little bit more complicated, but as you're playing around and trying to make new and different surfaces, you can, see what happens as you add more factors or more terms to your equations. And so the code looks pretty much exactly the same, right? The only thing that's going to change is these 6 lines. So let me copy and paste this and see what this looks like. If I replace those 6 lines, run it again. So it's like a little swirly pinecone looking thing. Again, this is relatively easy to do with parametric equations, but relatively hard to do if you were trying to come up with like an explicit formula for the surface or an implicit formula. The thought just occurred to me, but I think I've done that one before. So on the cover of your textbook, if you have a hard copy of the textbook, do you see that weird statue-looking thing behind them? Yeah. So I guess they didn't. Oh, they did. Okay. No, they didn't. So on a different version of this is the 7th edition, but I think like maybe on like the 6th edition, they actually put the formulas or the parametric curve equations for that curve on the cover of the book. And I think I've done it before in MATLAB, and so it's probably buried somewhere in here. I just gotta find. Yeah, I think they call it, the authors of the textbook called that shape an umbilic torus. And so if we copy and paste these lines of code, it might work, it might not work, but we'll try. Aha. So, yeah, so this is actually the shape that's on the front of your calculus book. And if you want to look at what the equations for that are, it's not terribly complicated, but oops, too far. But the formula for x involves some sines and cosines, and obviously u's and v's as my parameters. I said this before with parametric curves, but sine and cosine are periodic functions, and that means if you use sine and cosine functions only whenever you're determining your parametric curve, then it'll come back to where it started and you'll end up with a closed curve. I don't remember if you remember me saying that earlier this semester, but if you only use sines and cosines, you add sines and cosines, you multiply sines and cosines, or you compose sines and cosines, then you'll end up with a closed curve. The same thing is true with parametric surfaces. Like, these make nice, neat, closed surfaces because it's always sines and cosines that I'm, composing or multiplying, and so on. If you were to use other functions besides sines and cosines, sometimes you can get unbounded surfaces that aren't closed and they don't make nice, neat solids. But in this case, if you're wondering why all these turned out so nice, like the torus and this umbilic torus and the other things we've done today, it's really just because of those periodic functions make nice closed curves and nice closed surfaces. Ooh. Okay. So definitely try that. And we'll continue with the stuff you're supposed to know. So if we name our surface a little lowercase r, then this derivative, this partial derivative of r with respect to u, that would be a vector. It would be a 3D vector that's tangent to your parametric surface along, and it's going to point along the direction of increasing u, because again, we're talking about the partial of r with respect to u. So that's going to be a 3D vector where the first entry is the partial of x with respect to u, because remember x is a function of u and v. And then the second entry is going to be the partial of y with respect to u. And the third entry is going to be the partial of z with respect to u. You'll also see this written as lowercase r with a subscript u, where the subscript tells you to take the partial derivative with respect to u. Okay? Likewise, if we have the partial of r with respect to v, like this right here, same idea, but this is going to be the partial derivative of x with respect to v, the partial derivative of y with respect to v, and the partial derivative of z with respect to v. And that could be written as lowercase r with a little subscript v to tell you to take the partial derivative with respect to v. Remember way back at the start of the semester, we said that the cross product of two 3D vectors is always going to be orthogonal to the two vectors that we multiplied, right? So like, if this over here is the vector we call it A, and this here is the vector B. If I were to take the cross product of A cross B, or B cross A, either one, the vector has to be orthogonal. So if A and B live in the plane of my whiteboard, then A cross B has to be a vector that points directly out, or orthogonal away from the whiteboard. Okay? That was the fact about cross products. And we're going to use that in this section because if we have a parametric surface and you want to know a formula for a vector that is orthogonal from the surface, or you might say it's a vector that's normal to the surface. And we use both vocabulary words, but if you're ever asked for a normal vector, then the way that we would find a normal vector is by taking the cross product of these two partial derivatives, right? So if you ever see this show up, where R is my parametric surface, that cross product of two tangent vectors to the surface is going to be a normal vector from the surface. Okay? That'll be an exam question next week. I'll give you a parametric surface and I'll say, tell me the formula for a normal vector from this parametric surface. And you'll just be like, oh yeah, I know how to do that. I just take the partial derivative with respect to both of my parameters, and then I take the cross product of those two vectors. Okay, let's do, let's talk about tangent planes and then we'll do an example. Another question I could ask is, how do you find a tangent plane to a parametric surface? We give you like a torus or some other kind of parametric surface in space. And I ask you to find a tangent plane at a certain point along the surface. Step number 1 would be find a normal vector. And remember that the normal vector is just the cross product of those partial derivatives. And then step number 2 is that if you know what that normal vector is, I'm going to name it capital N for normal vector. So I've got this 3-dimensional vector. Let's call the entries A, B, and C. If that's my normal vector, then remember that the formula for a plane, the formula for a tangent plane, would just be A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. X naught, y naught, z naught is just the coordinates of a point along your surface. And then the normal vector A, B, and C is just the normal vector at that point along your surface. Okay? So we've already learned that earlier in the semester. You just kind of have to remember that and have that ready, memorized, ready to use on your exam next week. But that's the idea, is if you're trying to find a tangent plane, you first find the normal vector, then second, you use that normal vector in your tangent plane formula. Okay, so let's do this example. This is a really boring example, but I didn't have time to come up with a better one. I say that this example is really boring because this is supposed to be a parametric surface where, you know, x is a function of u and v, and y is a function of u and v, and z is a function of u and v, right? That's what it's saying. I say this is a really crappy example because you maybe can already tell if I wanted to rewrite this as an explicit surface, all I have to write is z equals square root of x times y, right? Because u is equal to x and v is equal to y. And so this parametric surface is just a really lame parametric surface. You know, it's too easy to just go ahead and explain this as an explicit surface. And we've already worked with explicit surfaces this semester. So I don't like this example. But like I said, I was kind of in a rush this morning, so this is what we have to go with. So step number 1, if we want to find a plane tangent to the surface, then I'm going to start by finding a normal vector. And so to find the normal vector, I would say, okay, first I'm going to find the vector where I take the partial derivative of r with respect to u. And that vector is going to be 1, 0, and then the partial of this with respect to u is going to be 1 over, yeah, one half times 1 over square root uv, and then times v, right? So we're treating v as a constant. I'm going to take the partial with respect to u. And then we would find the partial of r with respect to v. And that vector would be 0, 1, and then 1 half 1 over square root uv times u. And then, to find our normal vector, we're going to take the cross product of those two partial derivatives. And so I remember that the cross product is equal to the determinant of this 3 by 3 matrix-looking thing, where in the first row I could put 1, 0, and then v over 2 square root uv. And then in the last row I can put 0, 1, u over 2 square root uv. So I'll have I times 0 minus v over 2 root uv minus j times u over 2 root uv minus 0 plus k times 1. So this cross product, if I write it out in column form, has first entry negative v over 2 square root uv, second entry negative u over 2 square root uv, and then last entry 1. So if somebody is like, find me a normal vector, specifically at the point where x equals 1, y equals 1, and z equals 1, right? 1, 1, 1, that's actually x, y, and z coordinates, not u and v coordinates. Well, it's actually really, really easy to figure out for this problem. Maybe other problems aren't going to be so easy. But this tells me that x is equal to u, so that means u is 1. And y is equal to v, so that means v is 1. And so if I plug in u is 1 and v is 1, then this vector becomes negative 1 over 2, negative 1 over 2, 1. So that's going to be my normal vector to the surface at the point 1, 1, 1. Okay, how do we come up with the tangent plane now? The point where I want my tangent plane is 1, 1, 1. My normal vector is this one. So the formula for my tangent plane is going to be negative 1/2 times x minus 1 minus 1/2 times y minus 1 plus 1 times z minus 1. So that's the formula for a tangent plane to that surface. And I know that because these coefficients are the entries in my normal vector, and the x minus blank, y minus blank, those are the coordinates of the point where I want my tangent plane. Any questions about that example?
And that will be the answer?
Yeah, this equation down here, that's the answer to the question, find the tangent plane to the surface at the point 1, 1, 1.
That's what we're going to get on the exam, right?
Yeah, I'll give you a similar question.
See what problem.
Yeah. I started working on writing your exam. I'm not done with it. I might give you like a torus or a surface that's more interesting than that one, because like I said, this is like a really crappy example. You could have worked this problem as an explicit surface using your knowledge that you had before today, so I don't like that example, but
Gradient.
okay, so this is saying if you want to calculate the surface area of a parametric surface, right? You know your parametric surface, we're going to call it lowercase r. This is the formula you're going to use. And by the way, this little capital D, this D stands for domain. And so we're saying that this is my domain. Your domain is in terms of your u and your v parameters. So you got this little two-dimensional domain, so we've got a double integral. Your integrand is the norm of the normal vector. So that means if your normal vector is larger, then you're going to have a larger surface area If your normal vector is smaller, you're going to have a smaller surface area. The only intuition I could give is that this cross product is going to be bigger if either of those partial derivatives is larger. And a larger partial derivative means that your surface is more stretched out whenever you go from like u and v coordinates to being x, y, and z coordinates. In other words, like if you think of the u and the v domain as like a little square piece of fabric, and then you stretch it and you twist it and you rotate it and you deform it to go into the shape of your parametric curve. Larger partial derivatives means you're stretching the fabric farther in the u direction or in the v direction as you're deforming it. And if you stretch it more, that creates more surface area in your final curve. So this example has our little torus that we saw earlier that we put in MATLAB. So let's try to calculate the surface area of that torus using our formula that you just committed to memory, right? You just memorized that. So let's try to do this. The first thing is I need to take the partial derivative with respect to u, and that's going to be a 3D vector. So the partial derivative of x with respect to u is going to be not cosine, but negative sine. And then we pretend that v is a constant, so I don't actually have to do anything to that second part. That's all a constant. I can just say that this is negative sine of u times 3 plus cosine v. And then the derivative, the partial derivative of y with respect to u is going to be cosine of u times 3 plus cosine v. And then the partial derivative of z with respect to u is going to be 0. Okay. Then I'll take the partial derivative with respect to v. Again, a three-dimensional vector. This time, the partial derivative with respect to v is going to be negative sine of v times cosine of u. You're right, cosine of u times negative sine of v. Okay. Because if I distribute that cosine, then cosine times 3 is just a constant. And then I end up with cosine of u times cosine of v. And then again, we're only taking the partial with respect to v. So I don't care about the u's. I only care about the v's. The partial derivative of y with respect to v would be almost the same thing. It's going to be negative sine of u sine of v the partial of z with respect to v is going to be cosine of v. Okay, now we want to take the cross product so that we can find our normal vector. So ru cross rv is going to be the determinant of that 3 by 3 matrix looking thing. Where it's ijk. And then I'm going to need a lot more room. I might have to write pretty small too. So in the second row, I've got negative sine u times 3 plus cosine v. the middle entry of this matrix looking thing is going to be cosine u times 3 plus cosine v, and then the last entry is going to be 0 on the second row. Okay. Third row is going to have negative cosine u sine v. I just really hope I can read my handwriting after this. Second entry is negative sine u sine of v, and then the last entry is cosine of v. So when I go to take the determinant, this is going to be I times cosine of v times cosine of u times 3 plus cosine of v minus 0 minus j times cosine of v times negative sine u times 3 plus cosine v minus 0 okay. Just double check and make sure I did everything right so far. Okay, so far so good. Plus k, and k is times two negatives make a positive, so this is positive sine squared u times sine of v times 3 plus cosine v minus a negative cosine squared u times sine v times 3 plus cosine v. Okay. So that is our normal vector in IJK notation. And kind of messy, just a little bit. I see some things that might help us though, like specifically in this last entry, in the k entry, sine squared plus cosine squared is just 1, right? So imagine what it would look like to factor out the sine v 3 plus cosine v from both of those terms. And I would be left with sine squared u plus cosine squared u times sine v 3 plus cosine v. And so since sine squared plus cosine squared is 1, this whole thing simplifies to just that. Yeah, okay. Obviously I don't need those minus zeros. And two negatives makes a positive, so I can just do that. Okay, so just to remind what we're doing, this is the double integral over the domain of the norm of this particular vector. And this vector is RU cross RV. And that means I'm going to write out this vector in column form, and then I'm going to think about what it would look like to take the norm of it, because the norm of this vector is going to be my integrand in that equation. So writing this out and sort of distributing inside the parentheses, this is going to be cosine squared v plus... No, I don't actually want to distribute. Not yet. Not yet. So let me just go ahead and take the norm of this vector and write it in my integrand. So here we go. The norm means I take the square root, but then I square each one of the entries. So this is going to be square root of all this stuff, but I'm squaring everything inside. So I'm going to get cosine squared v cosine squared u times 3 plus cosine v squared plus cosine squared v sine squared u 3 plus cosine v all squared. Finally, plus sine squared v times, I ran out of room, but this is going to be times 3 plus cosine v all squared. This is actually working out pretty nicely, because if you look at the first two terms here underneath the square root, this first term is exactly the same as the second term, except this first term has a cosine squared u, and the second term has a sine squared u. I know that cosine squared plus sine squared is equal to 1, so I can factor out everything else and then multiply it by 1, and that simplifies very nicely. So the first two terms combined are going to be cosine squared v times 3 plus cosine v all squared. That's the first two terms once I simplify. Then the last term is plus sine squared v times 3 plus cosine v squared. And again, you're like, wow, cosine squared v plus sine squared v, that's just too good to be true. And so you can forget about all of that except for the 3 plus cosine v squared, which is nice because the square root cancels with the square, and then this integral becomes the double integral over our domain of 3 plus cosine v. At this point, we've got to choose an order of integration. Like, do we want to do du dv, or do we want to do dv du? Both of u and v have really nice constant lower and upper bounds. It's always 0 to 2 pi for both of those. So here's 0 to 2 pi, 0 to 2 pi. Let's go ahead and just knock out taking the antiderivative with respect to v first. And if that doesn't work, then we can always swap it and try again. So here's derivative of 0 to 2 pi of antiderivative with respect to v is going to give me 3v plus sine v evaluated at 0 and 2 pi. So if I plug in zeros, sine of 0 is 0, so the whole thing is 0. If I plug in 2 pi, sine of 2 pi is 0, so that goes away. And I get 3 times 2 pi, but that's just a constant, 6 pi. And so I multiply by 2 pi again, and I get 12 pi squared. So the surface area of our little torus that we plotted in MATLAB is 12 pi squared. That looked like it was going to be a bad problem for a little while. But it turned out really nicely. Do y'all have any questions about doing that formula? Okay. So yeah, I didn't close it. So last semester we did a fun little thing where we had like parametric curves in the XY plane, and I told you guys to like go home and make like a really pretty picture, and then we would like bring it back and vote on which one we like the best. We can do the same thing for more extra credit in terms of parametric surfaces. So all you have to do is copy this exact code into MATLAB Online at your place, and then this is the only part that you might have to edit, but you can keep the rest of the code the same and just put in your formulas for your x, y, and z as a function of u and v.